Hello, and welcome to the next video in my series on basic statistics. Now, a few things before we get started. Number one, if you are watching this video because you are currently struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you have come pretty far in your schooling up to this point, and you should be proud of that. The fact that you've hit a temporary rough patch doesn't mean you can't do it. So I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you, and so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. That does encourage me to keep making them, since I know they are beneficial. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to incorporate that into future ones. And finally, just keep in mind that these videos are meant for people who are relatively new to stats. So I will just be going over the basic concepts. And I will be doing so in a slow, deliberate manner. Not only do I want you to understand what's going on, but also why. So all that being said, let's go ahead and get started. So in my previous videos, I'll walk you through exactly what the Poisson distribution is. So if you're not sure exactly what it is or a little bit shaky about that concept, please go back and watch that video before you dive into this one. I'm not going to take the time in this video to re-explain something I already did in the previous video. So this video is about practice. We're going to apply the Poisson distribution to two practice problems, one involving a bank and the other one involving deer that get run over on the road. So that sounds exciting, right? So, thinking about those two examples and making sure you have the basics of the Poisson distribution under your belt, let's go ahead and dive right in. So here's the first example, and I call it Take It to the Bank. So a bank is interested in studying the number of people who use the ATM located outside its office late at night. So of course the bank closes at 5 or 6, but all of a sudden it's 10 at night, you're going out with your friends or your family or whatever, and you need some cash or whatnot, so you got to find the ATM, of course. So you go to the ATM at night so you can get banking services. Now, for many reasons, maybe, the bank is interested in the flow of people that walk up to the ATM. So they can look at the transaction history, they can look at the security camera, and they can figure out how many people arrive at the ATM for a given time interval. Now, doing that, what they found out is on average, 1.6 customers walk up to the ATM during any 10-minute interval between 9 p.m. and midnight. So they use the security camera or the transaction records in the ATM to figure out that on average, during any 10-minute interval, that could be from 9 to 9:10, that could be from 10:14 to 10:24, or 9:43 to 9:53. Any 10-minute interval, doesn't matter. They expect 1.6 customers to walk up to the ATM. The first question is, what is lambda for this problem? Second question, what is the probability of exactly 3 customers using the ATM or walking up to it during any 10-minute interval? So exactly 3. And finally, what is the probability of 3 or fewer, 3 or less people arriving at the ATM during any 10-minute interval? So of course, we got to have lambda. That's our first problem. Then we got to figure out exactly 3, and then we're going to find out the probability of 3 or less. So between 9 p.m. and midnight, which outcome, or the number of customers, is what we'd expect during any 10-minute interval? So, we could have 0 people arrive at the ATM. That's very conceivable. There could be a 10-minute interval in there, or anywhere, where nobody uses it. On the other end, we could theoretically have an infinite number of people arrive at the ATM. Now, in practice, is that going to happen? Well, no. But that is a characteristic of the Poisson distribution, is that the upper end of outcomes is theoretically infinite. And that's one of the things that makes it different from the binomial. So we could have 0 all the way up to infinitely many arrive at the ATM during any 10-minute interval. But what's the most likely outcome? What's the expected outcome? Well, if you remember in our problem, our expected was 1.6. The bank looked at its records, and it expects during any 10-minute interval 1.6 customers to arrive. Now, of course, that 1.6 is an average, so we're not going to have 0.6 of a human, or not a live one. So just think about the decimal there as an average, so that shouldn't freak you out. But our expected value is 1.6. Now, the thing about this is that the expected value, the mean, their mu, and lambda are all the same thing. You might see them used interchangeably in formulas, but in this case, they all mean the same thing. So 1.6 is what we would expect during any 10-minute interval. Now here is the graph of that distribution. So we have customer ATM arrivals with a lambda of 1.6. So it should make sense that the highest probabilities are around 1 and 2 customers. We expect 1.6 during any 10-minute interval. So you can see the probability of one customer walking up seems to be around 0.32, something like that. The probability of 2 customers walking up during any 10-minute interval is about 0.26 maybe. So that should make sense. Given our lambda, those 2 should be the highest. Now you can see we have 0, 1, 2, 3, and 4, and then it goes off from there. Very, very small probabilities. Now again, in theory, this graph goes on forever to the right, because we could have an infinite number of people walk up to the ATM, but in practice that does not happen. So we truncate our graph where the probabilities become so small that you can't even see them anymore. So I went ahead and made this 15, even though I could have made it probably up to 12, because the probabilities of 12, 13, 14, 15 customers walking up, while theoretically possible, are so unlikely they're practically 0. So just keep that in mind when you're looking at this graph. But of course the height of each bar is the probability for that outcome. So remember, in the Poisson distribution, lambda is the number of occurrences we expect over the specified time interval. So lambda is sort of the Greek symbol there, or it is the Greek symbol there, so get used to that. Now the expected value, the mean, mu, and lambda all mean the same thing in these Poisson distributions. So you actually may see mu substituted for lambda in some books, and that's okay. I prefer using lambda because it sort of gives the Poisson its unique identity, and you're not going to get it mixed up with something else. But they do mean the same thing. So as far as ATM arrivals, what's our lambda? Well, the bank expects 1.6 customers per any 10-minute interval. So lambda in this case is 1.6. And again, do not try to think of that as 1.6 divided by 10. That's not what that means. It's 1.6 customers per interval we specify. We would only change the customers if we change the interval. So lambda is 1.6. Now, what's the probability of exactly 3 customers? That's our first question. So here is the formula for the Poisson distribution. And, of course, the question is, what is the probability of exactly 3 customers during any 10-minute interval? So in this case, x is 3. That's what we're interested in, the number of customers walking up. That's our outcome we're interested in. Lambda is 1.6. We already discussed that. And then e is a constant. It is the base of natural logarithms. So I'm sure you've seen this in other math classes, and you've seen the button on your calculator. But e is just a constant that we used in this formula. Let's go ahead and substitute them into the formula so we can find our answer. So the probability of exactly 3 customers equals lambda, which is 1.6 raised to the x power, which is 3. So 1.6 raised to the 3rd power, times e raised to the negative lambda power, so e to the negative 1.6. And all that is divided by 3 factorial. So 3 is our number of customers, which is x factorial. Now we go ahead and evaluate that in the calculator, and we come up with 0.139. So the probability of exactly 3 customers walking up to the ATM during any 10-minute interval is 0.139, or about 14%. So here's our graph. It's the same graph we had before, but now we're going to sort of check our answer, the computation we did, with the graph. It's a way to double check to make sure everything's working okay. So the probability of exactly 3 customers we found out was 0.139. So if we draw a line over to the y-axis, that should intersect at about 0.14. And it does. So you can see the error there is a little bit below 0.15. So it would seem that our computation of 0.139 is correct, because that matches the height of the bar at 3. So again, it's a good way to understand your distribution. It's a good way to check your answer. And you can kind of see how it relates to other outcomes in the distribution. Now, how do you do that in the TI-83? And I'm sure it's the same in the TI-84, 85, 89, etc. Let's go ahead and figure out how to do that in the calculator. Well, the function we're going to use is the Poisson PDF. You got to be careful, because in the calculator there's a Poisson CDF that does something different. And we'll talk about that at a later point in this video. But make sure you're selecting the Poisson PDF. It requires 2 inputs, lambda and x, which is the number of occurrences we're interested in. So in this case, 3. To get to that, we press the vars button. That will take us to the distribution menu. Scroll down and you'll find the Poisson PDF. And again, be careful, because one says Poisson CDF. You want the PDF. Press enter. Then we'll type 1.6, comma 3, and we will have the Poisson PDF 1.6, comma 3 on the screen. Go ahead and press enter. This will give us the probability where x equals 3, or 3 customers. And again, that should give us 0.139. So the calculator actually has the formula stored in it. If we just tell it what lambda is and what our x of interest is, it will do the formula for us. So 0.139, that matches what we did by hand, and that matches our graph, so we're pretty sure that that is the correct answer. Now we're interested in the probability of 3 or fewer. So what is the probability of 3 or fewer people walking up to the ATM during any given 10-minute interval? So I've highlighted that there in the green. So 3 or fewer. That's 3, 2, 1, or 0. Now we call that the cumulative probability from 0 all the way up to 3. So if we add up the height of all those bars that are there in the green, that will be our answer. But of course, there's a function in the calculator that will do it for us. And that's in the same place we found the Poisson PDF, but this one's the Poisson CDF. That's the cumulative probability. And again, we give it our lambda, 1.6, and then the upper limit of our cumulative probability, in this case 3. So this will give us everything up to and including 3 as far as the probability goes. So when we evaluate that, we have 0.921. So if we add up the height of all the green bars, they will add up to 0.921, which of course is 92.1%. So the probability of 3 or fewer people walking up to the ATM during any given 10-minute interval is 0.921, or 92.1%. And this should make intuitive sense. Our lambda is 1.6. So that's going to be sort of the expected, or the mean. But of course, we're going to have some variation around that mean. So most of the probability should be centered around that mean. And if we go from 0 to 3, that's going to capture almost, not quite, but almost all of that. So it should make sense that it is that high, 0.921, because of what our lambda is. So answer summary. What's the probability of exactly 3 customers arriving at the ATM during any 10-minute interval? 0.139. What's the probability that 3 or fewer people arrive? That's the cumulative distribution from 0 to 3. And that is 0.921. So let's go ahead and look at our next question. Now I call this question, Fear the Deer. And while the problem data is made up, the problem itself is not. this is actually a problem I came up with because it's something I experienced dozens, if not hundreds of times over the years, because it's something I have to drive through a lot. So here's the question. The Indiana Department of Transportation is concerned about the number of deer being struck by cars between Martinsville, Indiana, and Bloomington, Indiana. And this is a real problem. Trust me. Now, they note the number of deer carcasses and other deer-related accidents over a 1-month period in 2-mile intervals. So they're going to look at data for a month, but they're going to do so by dividing the stretch of road into 2-mile intervals. So here's the road. Martinsville is at the north end. Bloomington is at the south end. And this is Route 37, in case you're interested. And the whole distance is 20 miles. It is 20 miles from Bloomington to Martinsville. So they take that road and they divide it into 2-mile sections. So 10 2-mile intervals. And of course, what they're going to do is they're going to keep track of the number of deer incidents, whether it's a deer that's struck and killed or just a deer that hits a car, but keeps on going, and the police are called nonetheless. So they're going to keep track of all those incidents, but they're going to sort of group them in these 2-mile intervals. And just so you know, this is actually the stretch of road. So I drive from Bloomington up to Martinsville a lot, and as you can see, it passes through quite a bit of rural wooded area. So you have the Morgan Monroe State Forest and Lake Lemon on the east side, and deer traverse through there because there is the Wabash River, I think that is, up there on the west side. So the deer go back and forth in this road. So it's a really big problem in real life along this road. So this is not something I'm sort of pulling out of thin air. But in case you were curious, this is actually it. So they collected the data, and here's what they found. In the first 2-mile segment, they recorded 6 incidents. In the next 2-mile segment, there were 0. In the next 2-mile segment, 2. Then 5, 9, 0, 4, 3, 5, and 2. So that is the data they recorded. Now we need to find the average number of deer incidents per 2-mile interval. So when we add all those up, that is 39 incidents. Now how many intervals are there? Well, there are 10 2-mile intervals. So divide by 10, and that comes out to 3.9 deer incidents per 2-mile interval. So what that means is that our lambda in this case is 3.9. So when we do subsequent problems, or as we answer subsequent questions about this, the lambda we're going to use is 3.9. So during any 2-mile stretch of Route 37, we would expect over this 1-month period, over a month period, to have 3.9 deer incidents in that 2-mile range. And again, the range doesn't have to be from 0 to 2 miles, 2 miles to 4 miles, 4 miles to 6 miles, etc. It could be mile 5.2 to mile 7.2. It could be mile 11.3 to mile 13.3. Any 2-mile stretch of road, we would expect 3.9 deer incidents over the course of a month. So here is that distribution. So we have the deer strike probability per 2-mile interval. We have a lambda of 3.9. And if you look, the probabilities are highest for 3 deer incidents and 4 deer incidents. And that should not, that should be relatively obvious why that is, with a lambda of 3.9. And of course, the distribution falls off from there. Just keep in mind, in theory, that an infinite number of deer could be struck on any given 2-mile interval, but of course that makes no sense in reality. But we just put it down there to make sure that we do realize that, in theory, it is infinite. Now on the other end, we have the probability of 0 deer being struck in any given 2-mile interval. And that's quite conceivable. So given any 2-mile stretch of road between Bloomington and Martinsville, it's quite possible that there are no deer incidents in that month. So that's within the realm of possibility. Then of course 1, 2, 3, and 4. Then it comes back down 5, 6, 7, and 8. So this is the graph we can work with when we're answering questions about the probability of any certain outcome or range of outcomes. So here's the question. What is the probability of 0 deer strike incidents during any 2-mile interval between Martinsville and Bloomington? So this is actually the 0 deer outcome. Now we can use the Poisson PDF that gives us the probability of exactly 0. Lambda is 3.9, and again x is 0, and that comes out to 0.02 or 2%. So the probability of 0 deer incidents in any 2-mile stretch of road between Bloomington and Martinsville is 0.02 or 2%. Now what's the probability of 9 or more deer incidents in any 2-mile stretch of road? Well, how do we find that out? Well, we know that the entire probability distribution has to be up to 1. So if we find the cumulative probability up to 8, we can take that and then chop it off or subtract it from the overall probability of 1, and that will give us 9 or more, the probability of 9 or more. Now when we do that, we know it should be a very low probability. Based on the graph we had, 9 or more deer is very, very rare. So we should know this is a small number, and when we find it out, it is. It's 0.018 or 1.8%. So the probability of 9 or more deer strikes in any 2-mile stretch of road is 1.8% or 0.018. Now here's sort of a question where we can talk about using this data to make policy decisions. And that's what stats is, by the way. We use stats to make decisions. So what values for X, of course, was the number of deer incidents, are beyond the 0.95 cumulative distribution? So we can start at 0, and we have a cumulative distribution that keeps going up and up and up and up. And at some point, we're going to cross over this 0.95 region in our cumulative probability. And our question is, where is that point? Well, if we do the cumulative distribution up to 6 deer incidents, we get 0.899. If we go up to 7, we get 0.956. So there between 6 and 7 is where we cross the 0.95 or the 95% cumulative distribution. So think about that for a second here. We would expect 3.9 deer in any given segment. But there's sort of a point where the number of deer incidents are going to be beyond what we would expect to happen naturally. Now we could pick 0.95 as that point. So I'm kind of doing so arbitrarily. This is not exact science. Again, this is just using data to make decisions. So if we pick the 0.95 point as, wait a minute, if this number of deer are being struck in this 2-mile interval, that is well beyond what we'd expect due to normal random variation. That's just too many. So what we can do is, knowing these probabilities, we might use the information to post warning signs. And I'm sure you've seen warning signs just like this that says, in any given 2-mile stretch, if we have 7 or more deer strikes, we're going to label that 2-mile stretch of road high risk. And I'm sure you've seen the signs. Deer crossing next 2 miles. So we would put a stake in the ground, a sign in the ground right there that says, warning, deer crossing next 2 miles, high risk, or whatever. Because we know that next 2 miles, the number of deer that get hit in that region are far beyond what we would expect to normally happen. So if we had 4 deer hit in that range, we would say, well, that's kind of what we would expect. But we would say, 7 or more, that's too high. Let's put up a sign. And again, I'm just using these sort of thresholds arbitrarily. And we might say that, between 5 and 6 or 5 and 6 deer, we'll call that medium risk. So we might say that, that is sort of beyond the 80% point or 0.8 in our cumulative distribution. So we might put a sign, warning, medium risk of deer crossing or whatever. But we can use these probabilities to make public policy decisions. And again, that's the point of stats, to make decisions. So using these 2-mile stretches, some data we collected, I'm sure, which is easily attainable because a lot of this stuff is recorded for safety reasons, we can make some decisions on what stretches of road are the most dangerous versus what is just sort of normal. Okay? Now, unfortunately, 3.9 or 4 deer per 2-mile range is a lot. It's not great. But given where the road goes through, that's just the reality. So we had to figure out a way to warn motorists. And we can use stats to do that. Okay, so that wraps up our 2 practice problems on the Poisson distribution. And again, I hope that this helped you see how this sort of area of stats can be used to solve real-world problems, to answer questions about the actual reality we live in. Help businesses make decisions, government make decisions, and all kinds of stuff. So I'm hoping you saw how it can actually work in practice and reinforce the actual mechanics of the distribution itself. So a few points before we wrap up. Number 1, just remember, if you're watching this because you are struggling in a class, I want you to stay positive and keep your chin up. The fact that you are on here learning, trying to improve yourself, is what matters. That's what's important. So always keep in mind that, hey, I'm here trying to learn. That's what's important. So stay positive and always look forward to what's coming next. And of course, most of all, I think, have fun learning. Number 2, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a video, you know about it. Give it a thumbs up if you like it. Give me a constructive comment if you think I can do better. So just hang in there. Stay positive like I always say. Realize that you can get through it. You should be proud of the hard work you've done up to this point. So keep practicing, be patient, and everything will work out. So all that being said, let's go ahead and wrap up. Thank you very much for watching. I wish you all the best in your studies, and I look forward to seeing you again next time.